Welcome to the deep dive. We're here to, cut through the noise and get right to the core insights. Today, we're diving into something absolutely fundamental, often working away totally unseen. Think about it. Every tap, every click, every single transaction, whether it's healthcare, e-commerce, maybe even those smart city sensor networks, it's all generating just mountains of data, billions of rows, petabytes. And if you're trying to make sense of it all, it can feel like you're, well, drowning, not just swimming. The real challenge is finding the valuable stuff, the gold, efficiently. So, our focus today, SQL optimization, specifically for big data analytics. SQL, it's still the backbone for structured data, right? No question. But here's the snag. When you hit big data, those SQL queries, they can slow right down to a crawl. We're talking high latency, wasted computing power, and maybe worst of all, missed chances for timely insights. So this deep dive, it isn't just about some techie trick. It's about why optimizing SQL is, well, essential for anyone dealing with data at scale. Our mission here, to give you a shortcut basically, help you get really well informed on the key techniques that make even massive data sets perform well. We want to unpack the important stuff, give you those, aha moments, clarify the tricky ideas so you can quickly get what's happening under the hood. You should walk away with practical insights, not feeling overwhelmed, but really appreciating the efficiency that's possible.
Okay, let's start right at the beginning then. When we talk big data, these huge data sets, billions of rows, complex queries, what actually happens if we just don't optimize? Why should someone really care if their query is running a bit slow? What's the real cost?
That really is the core question, isn't it? And the cost, it's definitely not minor. It spirals pretty quickly into a big drain, a bottleneck for decisions. See, without optimization, those SQL queries, they just devour time and computing power, way too much. Imagine a business waiting, maybe hours, for a report that should take minutes, or servers just churning away, CPU, memory, burning electricity, shortening hardware life. It all adds up. It directly hits how agile a company can be, how fast they react, and yeah, the bottom line. But flip that around. The benefits of optimizing, they're huge. First off, much faster query execution, like significantly reduced response times for analytics. And that's critical for real-time stuff, right? Market trends, monitoring systems, fraud detection. Second, you get really efficient resource use. Big win there. Optimized queries just need less memory, less CPU. It means less hardware needed, less power used, maybe a greener IT setup too. Third thing is scalable analytics. Your performance doesn't just fall off a cliff when datasets grow. And they always grow, so you can expand smoothly without constantly rethinking your infrastructure.
And maybe the most tangible bit, especially now with the cloud, everywhere, cost savings, real money. Think about AWS Redshift, Azure SQL, Google BigQuery. We pay for compute time, for resources used. Optimized queries mean less processing, fewer resources. It's often kind of glossed over, but we've seen companies literally have their cloud database bills, sometimes more, just by being smarter about their SQL. Suddenly, budget's freed up. Not by buying less, but by asking better questions.
Wow, having a cloud bill just through query optimization, that's not just a tech detail, that's strategic. It sounds like that ripple effect on resources and budget is way bigger than most people probably think. Okay, so if it's that important, how do we actually do it? What's in the toolkit to turn these slow queries into fast insights? What's the magic?
Yeah, it's definitely a powerful toolkit. Let's start with indexing. For faster data retrieval, think of indexes like, well, roadmaps for the database. Or maybe the index in the back of a book. Instead of scanning the whole library, the index points right to where the data lives, much faster. Typically, you're indexing primary keys, foreign keys, obviously, but also columns you filter on a lot, and your where clauses. And you can get more advanced, too. There's clustered indexing. That doesn't just point the way. It actually organizes the physical data rows on the disk based on the index. So related data kind of sits together, better access. Then you have covering indexes. These actually store the data needed for a specific query right in the index itself. So the database doesn't even need to look up the main table sometimes. If the index covers the query, bang, much faster, especially for queries grabbing just a few columns.
That covering index idea, that makes a lot of sense. It avoids that extra lookup. But I've heard people say, too many indexes can actually slow things down, especially for writes like inserts or updates. Is that still a worry with big data, or do the read benefits usually win out?
That's a really crucial point, actually. Yes, everyone knows about primary keys.
Yeah.
But the real skill is finding those other columns, the ones frequently filtered, and indexing them smartly.
Yeah.
And you're dead right. An index speeds up reads, but it adds overhead to writes. Every insert, update, delete potentially has to modify the index too. So the trick isn't just adding indexes everywhere, it's finding the balance. A read-heavy analytics system, it can probably handle more indexes than, say, a system processing millions of transactions per second. It's always a trade-off. tailored to how you use the data.
Got it. Finding that sweet spot. Okay, so beyond smart indexing, what's next for tackling truly massive data sets, the ones that are just huge?
Right, for those monsters, you look at partitioning and sharding, basically breaking one enormous data set into smaller, more manageable pieces. Imagine like a phone book for a whole country. Try to find one name. Nightmare. But if you split it into volumes, say one for each data region, much faster to search the right volume. And we usually talk about two main types. Horizontal partitioning, which is often called sharding. That's dividing the rows across different servers or tables. Each server holds a slice of the data. Then there's vertical partitioning. That's splitting the columns. Maybe you have a table with 100 columns, but most queries only need 10. You can split those 10 into a separate, narrower table. Reduces the data load for those common queries. This stuff is really effective in distributed systems, things like Apache Hive or Google BigQuery, which are built to handle data spread out like that.
Yeah. Dividing the phone book makes total sense. But I guess sharding, that must add its own headaches, right? Like keeping data consistent across shards, making sure queries go to the right place, handling schema changes. What are some of those maybe hidden challenges teams run into when they partition at scale?
Oh, absolutely. You've nailed some key challenges there. Partitioning makes queries faster, yes, but it adds operational complexity, no doubt. You need a good strategy for how you split the data. Is it by date, user ID, geography? And that strategy has to match your common query patterns, otherwise it might not help much. Then there's managing all these distributed pieces, data integrity, handling failures if one node goes down. It's powerful, definitely, but it needs careful planning and solid management. That's why you typically see it in really large-scale setups.
Right. Powerful but complex. Understood.
Oh.
So moving beyond the underlying structure, how much does the way we actually write the SQL query matter? Can that make a big difference too?
Well, massively. Query rewriting and optimization is absolutely critical. How you structure your query can have a huge impact on performance. It's not just about getting the right answer, it's getting it efficiently. A really basic foundational tip: stop using select at. Replace it with the specific column names you actually need. Select piece just forces the database to fetch every single column, even ones you don't use. That's a ton of extra I/O reading data from disks that's often completely unnecessary. Another big one: use joins wisely. Often they're better than complex subqueries. Subqueries can feel intuitive when you're writing, but database engines are usually much better at optimizing join logic. And for calculations like sums, averages, ranks, look into window functions. They can often replace nested queries or self-joins, and they're usually way more efficient. They let you calculate over a window of related rows without complex grouping. And finally, simple stuff. Avoid distinct and order by if you don't absolutely need them. Sorting large datasets, very resource intensive.
Okay, mental note. Ditch Siglakity unless absolutely necessary. Those are really practical tips people can use straight away. But what about queries that run over and over? Like for dashboards or regular reports, is there a way to make those faster beyond just optimizing the query itself?
Yes, exactly. For those repetitive, complex queries, materialized views and caching are your friends. A materialized view is basically, well, it's like taking a snapshot. The result of a complex query is pre-computed and stored as an actual table. So instead of running that heavy join or aggregation every single time, the database just reads the pre-calculated result. Huge speed boost. Combine that with caching, keeping those results in fast memory, you get super responsive dashboards, even with complex underlying data. Then there's the power of the engines themselves, parallel query execution and distributed processing. Modern systems think Snowflake, Redshift, Spark SQL, BigQuery, they're built for this. They automatically break down your complex query into smaller tasks, and then they run those tasks in parallel across lots of processing nodes simultaneously. That's how they can chew through massive data sets so quickly. It's divide and conquer, but for computation.
Right, a massive divide and conquer strategy built into the database itself.
Yeah.
How much of that parallel stuff does an engineer need to manually set up versus what these modern platforms just handle automatically now?
That's a great question, and it highlights a big shift. With older, maybe on-premise systems, you might have spent a lot of time manually figuring out partitioning or giving hints to the query planner. But with a lot of the modern cloud data warehouses and platforms, a huge amount of that parallelization is just automatic. The platform's optimizer is smart enough to analyze your query, figure out how to break it down, distribute the work across available nodes, and bring the results back together. Your job is more about writing good, clean SQL. The platform increasingly handles the complex distributed execution part. And one last piece, often working quietly in the background: compression and storage optimization. Big data usually means lots of repeated values, right? Think a country column with USA appearing millions of times. Columnar storage formats, things like Parquet or ORC, are common examples that are designed exactly for this. They store data column by column, not row by row like traditional databases. This lets them compress repetitive data incredibly well because all the USA values end up stored together.
Better compression means less data to read from disk-reduced I/O, which directly translates to faster queries. It's a fundamental boost right at the storage layer.
That's a really comprehensive toolkit then. Optimizing storage, the query itself, how it's processed, even pre-calculating results. It's clear this is way beyond just fiddling with settings. It's about rethinking how we interact with data at scale. So let's bring it back to the real world. What does this actually mean for people? Where are these techniques making a real, tangible difference out there?
Right, this is where it gets concrete. In healthcare, for example, optimized SQL means faster processing of huge patient record datasets. That's vital for things like predictive diagnosis, identifying disease patterns early, maybe even predicting outbreaks faster. Speed really matters there. In finance, it's huge for real-time fraud detection. Analyzing massive streams of transactions as they happen to spot anomalies requires incredibly fast, optimized queries. Protects everyone. For retail and e-commerce, think about personalization. Those product recommendations you see, they're powered by efficiently querying your past behavior, clicks, purchases. Good optimization means better, faster recommendations, which drives sales. And then there's the whole IoT and smart city space, analyzing floods of sensor data in real time. Whether it's managing traffic, optimizing energy grids, predicting when infrastructure needs maintenance, all depends on fast analysis of massive streams. Optimized SQL is foundational. It enables smarter decisions at a citywide, even societal scale.
Yeah, it's clear it's not just shaving off seconds. It's enabling whole new capabilities, pushing industries forward, real value creation. Okay, this is all super powerful now, but what's next? Where's this heading? What does the future look like for SQL optimization with data just getting bigger and bigger?
It's definitely not standing still. It's evolving fast. A big trend is AI-driven query engines and automated indexing. We're seeing systems that can learn from query patterns and automatically suggest or even create the optimal indexes, or rewrite queries behind the scenes. It takes a lot of the manual tuning effort away. Tied into that is the rise of autonomous databases. Think Oracle's Autonomous Database, or some features in Snowflake and others. These platforms are increasingly self-tuning, self-managing. They monitor performance, adjust configurations, optimize queries automatically. The goal is to let data pros focus less on the plumbing and more on the insights. But the really big picture trend, looking towards, say, 2025 and beyond, is the synergy of SQL plus AI. Using AI not just to optimize existing SQL, but maybe even to help generate more insightful queries, to understand the data more deeply, and handle unprecedented scale and speed for real-time analytics. That combination is going to be key.
A self-optimizing database world? That's quite a vision. Though I suspect there'll always be a need for that human expertise, that intuition, even as AI gets smarter. But regardless, this deep dive really hammered home that optimizing SQL for big data, it's not some optional extra. It's a strategic necessity for any organization wanting to be competitive, wanting to be insightful in this data-flooded world. So as you, our listener, navigate your own data puzzles, maybe take a moment to think about these hidden levers of SQL optimization. How could understanding this stuff maybe change how you approach getting insights, or even how you make decisions based on data?
Yeah, and I think this shows that even with really complex tech, getting a grip on the basic principles gives you power. Power to ask smarter questions, build better, more efficient systems. It's not just about speed, ultimately. It's about getting a deeper, more meaningful handle on the data that's shaping so much around us and the tools we rely on to understand it.
Well said. Thank you for joining us on this deep dive. We really hope you found these insights useful. Until next time, keep digging for that data gold.